Together, we call them as electron domain. So this is actually lone pair plus bonding pair. We can abbreviate bond pair as BP and lone pair as LP. Electron domain is nothing but the area of high electron density within the molecule. Right. So here we will see one by one examples that how can we predict the shape of any given complex molecule or ion. Let's start with example PCl3, phosphorus trichloride. So our first step is step 1. We will write the Lewis structure. So let's write the Lewis structure. Now we know that phosphorus contains 5 valence electrons. Out of the 5, 3 are being shared to form 3 covalent bond with 3 chlorine. So I can say like that, and here I can take chlorine like that. So I can write the Lewis structure something like that. Each chlorine is having 1 covalent bond and 3 lone pair each, and phosphorus, which is the central atom, is having 3 bonding pairs and 1 lone pair. Here we should keep in the mind that it's always the central atom. So it's important to note down, with respect to central atom, we predict the shape. All right, so here let's count the lone pair of phosphorus. So phosphorus has 1, 2, 3. 3 bonding pairs of electron and just one lone pair. So total electron domain, count of electron domain is 4. Now, with respect to the electron domain 4, our shape should be tetrahedral. Here, but the shape is pyramidal actual shape because of the presence of a lone pair. So as per the VSEPR, lone pair creates repulsion. That's why the actual shape of the molecule is not the predicted one. Based upon the number of electron domain, it is supposed to be a tetrahedral structure, but actual shape is pyramidal. So here we have to understand the electron domain geometry will be tetrahedral only. But the actual shape is called pyramidal. Now let's draw the structure. So now see, this is phosphorus with a lone pair, and this is the molecule, which looks like a pyramid, hence pyramid. Okay, this molecule can be represented in 3D format also, something like that. It's the same thing, same structure. We call this structure as pyramidal structure as it looks like if I look for the shape like so, just it looks like a pyramid, hence called pyramid. Next shape we can talk about is, next example we can take is XeF4. Now again we will write the Lewis structure. So xenon is an inert gas and it has total of 8 valence electrons. So I can write something like that. 1, 2, 3, 4, 5, 6, 7, 8. And then I can have fluorine, which we can take in this color. So 1 fluorine, another fluorine, the structure can be written like that. All right, let's count the domain. So xenon is the central atom here and it has 1, 2, 3, 4. 4 bonding pairs plus 2 lone pair. The total domain makes it 6 electron domain. All right. Based upon the number of electron domain geometry, 6 electron domain refers to a regular octahedral structure. So it is electron domain geometry is octahedral. But the actual shape again is different because of the presence of 2 lone pair. Actual shape is called as square planar. How come? Let's see the shape now. So if this is the xenon, then so these are the rear fluorine atoms, these are the front fluorine atoms, and these are the 2 electron pairs, which are lone pairs. So we can imagine this shape as this is actually a square-based structure. 1 lone pair above the plane of the square and 1 lone pair below the plane of the square. This makes the structure as square planar structure. We can look for the shape again here. So let's look for the shape. This is the shape. Right? Next example we can look at is I3 minus. It's a polyatomic ion. So as I told you, we should write the Lewis structure first. Let's see. Here central atom is iodine and the terminal atoms are also iodine. Each iodine contains 7 valence electrons. So out of the 7, 2 are occupied here. 1, 2, 3, 4, 5, 6, 7. So we can see this iodine contains 2 bonding pairs but 2.5 lone pairs. So half lone pair does not make any sense. Now, since this molecule contains 1 negative charge, so this negative charge imparts 1 extra electron. And it is this extra electron which makes the electron count complete for this iodine, central iodine. So this is my Lewis structure. So electron domain are, so central iodine has 1, 2, 3. 3 lone pair plus 2 bonding pair. So total 5 domain. And so electron domain geometry will be based upon 5 means it should be trigonal bipyramidal. But hence again, for a proper regular trigonal bipyramidal shape, I need 5 bonding pairs, and here we have only 2 bonding pairs. So we can write the structure something like that. The 3 positions of the triangle of this triangle are occupied by lone pairs, and just the top and bottom position above and below the plane of this triangle are occupied by the iodine atoms. This is referred to as a linear structure. Actual shape is called linear. Right? Okay, let's see one more example here. Next example we can talk about is, let's take one more ion here, which is we can take PCl4 plus this time. Okay, so let's write the Lewis structure again. Phosphorus has 5 valence electron, but since it is a cation, a plus charge, that means 1 electron is just missing. So the total valence electron for phosphorus here are just the 4 electrons, which all 4 are involved in the covalent bond formation with 4 chlorine atoms. So I have only 4 bonding pair and 0 lone pair, which makes it 4 domain total. And electron domain geometry as well as the actual shape, both will be same. That is tetrahedron. Now we can draw this molecule in a regular tetrahedral manner. A regular structure. Let's take one more example. This time we can talk about SF4. Let's write the Lewis structure again. So sulfur has total of 6 valence electron. Out of 6, 4 are occupied in the covalent bond formation. So here is the, let's take the fluorine. Okay, let's take another color here. Let's take this color for fluorine. Structure will be something like that. Now let's count the domain. 1, 2, 3, 4. So I have 4 bonding pair plus 1 lone pair, which makes total of 5 domain. Therefore, the electron domain geometry will be trigonal bipyramidal. But because of the presence of a lone pair, the actual shape will be different. Actual shape is called as seesaw. Let's see the structure. This is sulfur. This is 1, 2, 3, 4. These are the 4 fluorine atoms. And this is the lone pair. The shape is called as seesaw shape.